Hello, everyone. Welcome to today's webinar on the topic of developing, printing, and testing high-performance osseointegrative spinal implants. My name's Sean Cashman. I'm a sales development representative here at nTop. The webinar today will be about 30 minutes long with 15 minutes at the end for questions. Um, if you have any questions during the presentation, please feel free to put them in the chat or the Q&A, and we'll get to them at the end. We have three presenters with us today. Would you guys like to introduce yourselves?
Sure. Hi, I'm Mandy Rosengren, Senior Solution Engineer here at nTop. And I've been at nTop in the customer success team for over 3 years now, and I'm based in Boston, Massachusetts.
Good afternoon, everyone. My name is John Laureto. I function as the business manager for Renishaw Inc.'s additive manufacturing product line. We're based in West Dundee, Illinois, which is just outside of Chicago. I've been with Renishaw for 7 years and in the laser powder bed fusion game for almost 12 now.
And hi, I'm Shane Keaveney. I'm from R&D manager here at Croom Medical. We're based in Limerick in Ireland. I've been with Croom for about the last 5 years and been working in additive for about the last 10 years. So.
Great. Thank you, everyone, for introducing yourselves. Now we'll go ahead, look at today's agenda. So first off, from nTop, Mandy will be talking about, designing medical implants in nTop. Then we'll follow up with John from Renishaw to speak on vertical integration and manufacture. And then following up then, Shane will join from Croom to discuss application areas for nTop and Renishaw. And then at the end, we'll have that Q&A session. So with that being said, Mandy, would you like to take it over for nTop?
Sounds good. So yeah, before I go into, what you've all came here to see, the implant, I will first just give a brief overview of nTop. So at nTop, our mission is to develop powerful computational design tools that enable creators to accelerate innovation and deliver products the world needs. And so we're here to help engineers unlock innovation in a way that isn't possible with the tools many of them use today. That being said, we know most engineering teams have long-established tool sets and workflows, and we can integrate with those tools, bring in CAD, export mesh, export slicing, and we'll talk about some of that integration and export later today. In addition to the application we're talking about today, implants, we have many other common applications that our customers use nTop for, including lightweighting, thermal management, fluid management, mass customization, energy absorption and comfort, and acoustic vibration and radio frequency. But let's focus on today using lattice structures and our simulation tools for designing medical implants in nTop. And if you want to see a bit of a more of a deep dive in this process, especially on the design side, being able to adjust all your parameters and really kind of dive into how this workflow is being developed, we have another webinar on our website that you can really see the design side in depth. So this is really more of a summary of how we can build that geometry and simulate it and export it. So I'll go through a demo in nTop in a little bit, but just to summarize, first step is designing the implant. And I'll go through how we can generate a Voronoi lattice structure in these inner lattice geometry, as well as periodic lattice that we can see on this, what I've labeled in pink, but I labeled that kind of outer lattice structure. And then what we'll do is then union those two types together, as well as the solid geometry for our final part. Then with nTop, we have the capabilities to create what we call custom blocks, but you can think about it, you have a any programming experience thinking of it as a function where we can generate our own function or custom block that we can change parameters pretty easily. And, we don't even have to kind of see all those steps or repeat those steps that I'll walk through today. And with that, you can iterate, change the parameters that you're working with, whether it's point spacing, thickness, and see what's the best design for your use case. And once we've done those iterations, once we've created that design, the next step is simulation. So I'll also go through our static structural analysis and showcase how we would set that up, showcase it on a couple other parts. And then later we'll see some real world compression testing as well. But with that, and of course, connecting the nTop software side to then getting this part out into the real world, I'll also talk about exporting and how we can go about that. But let's see it in nTop. Let's see what's actually happening. So first, we have to do that design step. And the first thing I always recommend is splitting up the parts based on what you want to do with those different sections. So I have my outer design space in green, my solid regions that I'll eventually combine everything else to, and then I have my windows that'll add the Voronoi lattice in this example. So the first thing I do is apply a Voronoi, that kind of random structure or osseointegrative structure. And I'm going to be generating it using a set of random points. And that's how I can define that porosity. I create that Voronoi volume lattice so that it's also within that region. I can define that as the boundary. And then for any of the lattice that is exceeding our window design space, I can then trim that lattice. So I have my first step here. Then I also have to generate the periodic lattice. So I am using a periodic lattice block to do so. And I can adjust the different lattice structure that I want to work with, the unit cell size. I have that all in my input section of my nTop notebook. And as we can see, this is exceeding our outer design space. So just as before, I'm going to trim that lattice so it's within the design region we want. And now that I have those both generated, I can union the three sections, the inner lattice, the outer lattice, and the solid regions all together, and then use a Boolean intersect to remove any parts of that lattice structure geometry that's maybe exceeding our design space. And that's how we get our kind of generated lattice here and implant. And again, you can check out our previous webinar for more of an in-depth walkthrough on that whole design side. Now, once I have my workflow set up, if I want to apply something like this to a family of parts, or I want to, iterate and decide what is the optimal lattice thickness, or test out different types of lattice structures, what I can do is create that custom block, that function that I had mentioned earlier. And so I've already demonstrated, I've created this block, this custom block called lattice implant. And if I open this up, this is going through the exact workflow I just summarized just before, but now I have the inputs that I'm going to adjust. So I will adjust the lattice thickness for our inner geometry and our outer lattice thickness as well. And my output will be this final lattice that I want to have as the result. So with that, you can see all of those steps that I've done above are kind of hidden within that function, within that custom block, and I can adjust those like so. And what I can do is then I've created a set of different inputs for the outer lattice thickness and the inner lattice thickness. And if I visualize this, we can see I've now generated many of these different lattice structures. So we can see I'm viewing this in medium resolution, so we'd see it a little bit more crisply in a higher resolution, but just for the speed of showcasing this, we have that inner lattice, the thickness is changing, and then we have the thickness of the outer lattice changing. And then we could export this, run through different simulations, print different options and see what's the best one for our application. So speaking of export, if I'm ready to print this, for instance, go back to just this one part that I'm working with. We have a lot of different methods for exporting a part outside of nTop. You could, for certain applications, export the implicit directly, export a mesh, or to save some of that file size, save on time. We also have the ability to create the slice stack. So you can either export the body itself, so I can slice that whole geometry, or I can also slice individually that solid geometry that I've defined above in those solid regions. And then I can use our slice graph, which will slice the lattice structure. So graph you can think of as basically the unthickened lattice structure. And we have a set of points that showcase that lattice structure in space, and we can cut that and create those slices for each of the layers. Then we can merge those two together and export that, for instance, export the slices to Renishaw, which we'll talk more about that connection in a little bit. The last thing I'll briefly kind of touch upon is then running through a simulation. So later we'll see some real compression testing with these physical parts, but we can also run through that simulation within nTop. So if I look at this other notebook, I have the same setup from before. I have my final lattice, but now I want to run through that structural analysis and see what the result is. So what I'll do is create my FE volume mesh. I also have these two cylinders that I'll use to kind of replicate that compression testing that we are doing, and run through my static analysis, defining my boundary conditions as a displacement restraint at both of those cylinders, and allowing some room for that movement to replicate that compression testing. And if we see the static analysis, you can already see that deformation scale, and I can see how that would look. I can also view the strain and the stress, and I can adjust the range as well to get a better kind of visualization of our weak points that we have here. And just as we had talked about that iteration in the design side, we can use that same type of process to quickly run through different static analyses on different parts. So while this is showing that Voronoi lattice that I had shown before for the inner lattice geometry, we can also apply this to, for instance, the diamond lattice at the inner lattice window. I also have the TPMS structure that we can see that deformation scale and see what that would look like, as well as our face-centered cubic. So just a brief overview on the different steps that we have for generating those lattices and running that simulation. And with that, and going back to the next steps after you've gone through your simulation, you've gone through your design, is export. So I'll pass that on to John to talk a little bit more about Renishaw.
Thank you, Mandy. All right, so Renishaw in this example here is the hardware provider to Croom. Okay, so there's a couple things that we're going to touch on in the AM context, but I also want to make sure we all have a full understanding of what Renishaw does from an entire manufacturing portfolio suite. Our core competence is in design and manufacture precision metrology equipment. So as you scale that and think about that from even a subtractive context, that gets into things like CMMs, machine tool probing technologies, laser interferometry, and even medical device manufacture in the AM context, okay? So being that a lot of CMM technologies and laser interferometers leverage optical-based measurement capabilities, that puts us in a unique position to be able to support AM equipment, specifically laser powder bed fusion, because, well, they use lasers, right? So with that, you can kind of integrate and find that we have a large vertical integration capability within Renishaw to be able to leverage our own technologies that we sell into the market, into general manufacturing, to build them up into our own AM product lines that we would supply to Croom and others, right? So by consequence of that, from an internal R&D perspective, and moreover, what that does to support our customers in the field is that internal ability to do that research and development is a reciprocal benefit, not only for our own technologies, but also for the customers, i.e. they can scale with Renishaw technology. So to further go into Renishaw a little bit more detail is to show you the scope of not only our impact in manufacturing, but also our global initiatives. While we are UK based, we have subsidiaries in 36 countries, all around the globe. We're about 5,000 people. This year, the fiscal quarter results for 2024, are just under 600 million pounds. And back to what I alluded to prior, we're always very proud of the amount of R&D revenue that we leverage for our own internal purposes based upon that whole vertical integration reciprocal benefit story I was alluding to prior. So relative to Renishaw in the AM context, I think it's important to understand where we came from in that regard. So back in 2008-ish era, Renishaw was an end user of laser powder bed fusion equipment. We had a product line called our medical dental division that leveraged single laser and were called AM125 systems at the time. And we use that equipment to manufacture dental products. So think like crowns, caps, abutments, and even removable partial dentures. At that time, Renishaw, being a metrology company, had identified that the technology at that state wasn't really up to task or par with what's necessary from a manufacturing context. And that's when we decided to kind of start spending some capital and money on this type of technology. We invested in the company we were actually originally purchasing machines from. It was called MTT Technologies at the time. So since then, Renishaw has thrown around its engineering might to develop our own AM equipment with that original technology. And in 2017, we had to launch what we call our flagship product, the Renishaw 500. And over time, we've been slowly integrating new technologies into that support the customer from a robustness of manufacturer perspective, and also increase productivity and things of that nature. So one thing to be cognizant of there is like our Tempest technology, which I can get into in a bit more detail if there's any questions, but that provides a significant productivity benefit that's only enabled with the ability to have a vertically integrated AM machine platform. So relative to the 500 series itself, just to run through that quickly, there's 3 different types of packages that a customer could leverage. Croom specifically is leveraging a Renishaw 500S machine platform. So the flexible systems are meant to be total loss powder management systems. So powder on the top goes through the build chamber for the printing process, comes out the bottom, you go sieve offline. The standard S&Q is our default machine platform that would have our internal powder recirculation capabilities, so onboard sieving, and it leverages the exact same build envelope, size, space, and function that the Flex would do. So it allows for that progressional step from, say, more of an R&D, bespoke production type stuff on the Flex machine to a more productionized scale application with internal sieving on the S&Q. Then the Ultra is when the customers really need to turn up the speed from a manufacturing perspective, and they want to leverage things like that Tempest technology. And it also includes our in situ process monitoring solutions that I'll get into in a little bit later in the slide deck here. So as I alluded to prior, in the medical dental for us in the printing world is typically cobalt, chrome, and titanium. So there's some common examples that we deal with on a day-to-day basis are dental frameworks, RPDs, spinal and orthopedic implants, things like tibial trays, acetabular cups, and obviously spine in the case of Croom. And then also we have a pretty large install base in the craniomaxillofacial CMF world as well. Okay. Now on the 500, there are a wide variety of technological benefits. I'm not going to get into all in this presentation just due to time, but there are a couple of key ones I want to call out that specifically benefit medical device manufacturing, Croom specifically. So one would be on the top left, gas flow through in the system. It's a core principle of how we've designed the machine. It helps us maintain proper metallurgical integrity of the welding process and keeps the optical window clean to ensure good laser quality. Moreover, that gas flow is recirculated in the system through an intercooler, which helps us maintain not only gas flow temperature, but helps exhaust, condensate, spatter, and things of that nature throughout the welding process. But maybe even more importantly, helps maintain optical control and stability of the optical module and laser systems, i.e. Things like scan field, power mapping, beam profile, and focus of the laser, for example. The last little bit here I think to concentrate on is the bottom right-hand side of the chart. Back to my point prior about expertise in optical-based measurement capability. The optical module on top of the Renishaw 500 series is a Renishaw designed and built module. We actually leverage a ALSI 10 printed galvo block, as we refer to it, that allows a single up to a quad laser system to all be integrated within one thermally managed unit, which again helps with optical stability. And moreover, it mitigates the necessity for F theta lenses. So relative to lasers addressing the build plate, each laser can go across the build plate at any given time with complete overlap capability. So theoretically, each laser could be one on top of one another across the plate as necessary if that was applicable to what you need to do. Moreover, designing of the optical train from internal to Renishaw also gives us the capability for Croom to leverage, say, a modulated approach strategy to their assignment and or continuous wave. So Shane will get into that in a bit more detail, but there's bespoke situations where both might be applicable, only one versus the other. But the fact that the user has control and access to that is a big deal from an end user perspective. Now, outside the machine platform, there's a couple of tools to be aware of that Croom will leverage in their quality processes. So think like Infinium. So that's what we call our in situ monitoring package. So we have our Infinium camera, which I'll get into, and our Infinium spectral, which I'll dive into more detail. And then Renishaw Central is our 1D sensor data collection tool, so things like O2 sensors, things like that, time series plots. And Quantum is the build preparation software that Croom would leverage after extracting a slice stack or CLI file from the nTop software. And I'll touch on that briefly. So camera, just to go through this quickly, there's a white light photography camera within the build chamber that'll take a picture of the layer after a dose has been completed and a picture of the layer after a scan pass has been completed. So after the laser is done welding. Over time, across a 2000 layer build, if you will, we can end up stacking those images and turn them into a grayscale and identify a mean RMS, root mean squared distribution of gray, if you will, across each of those profile sets. So while this isn't necessarily quantitative data, it allows the end user to identify quantitative or qualitative metrics, excuse me, to identify if there's any deviation within the build sequence, right? So take like the powder bed as an example. If say a spinal implant delaminated from the build surface for some reason, the grayscale image would light up quite a bit for the powder bed, and that would identify to Croom that there's an issue potentially, right? Relative to Infinium Spectral, this is more of the laser-based in situ process monitoring solution. So a bit more clever than the white light photography system I described prior. But the main principles here are that we have a laser that on our systems that shoot 1070 nanometer approximately in wavelength. And we have photodiode sensors in the plasma realm and in the melt pool realm. So this is a quick system architecture of the optical module. So on the left-hand side, left of the collimated lens here, you have that primary optical module. On the right-hand side, you have the an attachment that would be on the Ultra systems for what we call our melt view module. So in the laser view module, that's confirmation of Croom to be able to confirm that if a laser has been demanded 500 watts, we can actually measure if the laser is outputting 500 watts at time of demand. So there's a photodiode system before it even goes through the entire optical train and incidents to the bed. Okay. Now on the melt view side, it's a literal thing. It's looking at the melt happening live. So as laser would come down through that primary optical path, as we had talked just slide previous, any of the back reflected IR and or plasma realm that would come up to the optical train, we can get positional feedback from the galvos, the same ones it came down on effectively. And then it can back reflect up into the melt view photodiodes, which you can calibrate different wavelength frequencies based upon what we're doing. Okay. So overall, what that allows you to do is capture that data in a pixel or voxel representation, i.e. 2D or 3D, depending on how you want to look at it. There are some resolution constraints with that, but overall, what this tool is designed to do is provide the end user with a visible, and or you could go quantitative with it as well if you want to extract the data. It's a bit more labor data resource heavy, but overall, that's what that's designed for. And it gives the end user a practical representation or a gauge of how the build went. So how we would like Croom and how others have leveraged this in the past is to say, okay, we have the spectrum that we've collected from this qualified build artifact that has a mountain of empirical data and process testing, like Mandy had alluded to prior. And then any build thereafter can be compared to that spectrum or spectra, and then basically post-process validated to confirm that the build process went the way it's supposed to go, right? There's no significant deviation. And like the images on the right-hand side show, there are some more, again, like I alluded to, quantitative metrics you can leverage from the perspective of you could identify, lack of fusion defects and keyhole phenomena if you choose so. All right, and central quickly, we have, like I alluded to, 1D sensor data. As machines running, you get current status, productivity, job performance, and real-time monitoring of any sensor that's on the machine platform. Good to generate build reports and things of that nature, critical to the quality metrics, QMS system you might have in your system and your manufacturing environment to confirm robustness of the parts coming off the machine. And then, of course, we have Quantum. So in Quantum, that's our build preparation tool, or a slicer as we refer to it. Quantum can take step by just parasalad, but it can also take native slice stacks from nTop and or CLI files. And then within Quantum, that allows Croom to leverage the capabilities of the parameter development, utilities, CSV modification of the parameters, because everything's open in Quantum. There's nothing locked down from a parameter set perspective, and they can apply modulator continuous approach strategies as they need to all across the bed. And there's an image here on the slide just to kind of give an example of how you can individually interpret point exposures at different build styles throughout the geometry. Because certainly the lattice structure might have a different parameter set than, say, the border, of a different volume that Mandy had alluded to prior. So overall, if you consider all the platform packages we talked about, we're going to have your design of the part, you're going to have your process parameters defined, and all your quality metrics coming through the system in either the in situ process monitoring data or Renishaw Central. allows you to develop a first article, and then function from the first article, continuing to monitor that data allows you to go into a formal productionized solution. And I think that's exactly what Croom is going to be talking about here moving forward, how they leverage this technology in the production context. And I'll pass it off now to Shane to continue his bit.
Thanks so much, John. Yeah, I'm just going to talk a little bit here about what Croom Medical does, who we are, and the type of kind of applications we have for nTop and Renishaw's additive tech. So really just to give you an insight into sort of the application areas for these. It's a little bit about Croom. We're a contract manufacturer, as I said, based in Limerick in Ireland. We focus mainly on orthopedic implants, but our expertise are in joint replacements, spine, foot and ankle, trauma, and extremities. We are a second generation family owned company, and we'll be 40 this year. We're set up in 1984, and our 24/7 production, 170 plus people working there at the moment. I think main thing to note is that we do supply mainly into the US, so we're FDA audited facility. We do have ISO 13485 as well, but very familiar with the FDA, how that works in terms of 510Ks and the regulations and how to manufacture within that regulated environment. Just in terms of high level investment, you can see 2019, 2020, we had quite a large amount of investment in here to help our expand and to grow as well. We've had some other investment rounds there as well, and then we're projected around 8 million euros investment in the next 2 years. So I think just to see what Croom does, I have a short video that I'll talk through. And so this is our facility here, just shows our location in Limerick, Ireland. As I said, some of our example components. So we do a lot of work on femoral components, so grinding, polishing, 5-axis milling, mill turn mill, sliding head type operations as well. So we have a huge expertise in machining of kind of exotic or difficult to machine materials such as titanium, cobalt, chrome, these types of things. And also quite a lot of expertise in small features, so small component manufacturing, as well as our sort of femoral grinding and polishing. I think an area that's super critical when we look at something like a femoral knee component is that polished surface. So we have, again, a lot of expertise in there. We have a lot of expertise for hand finishing and polishing, but also we're working on the automation of some of these processes, particularly these difficult labor intensive sort of polishing or finishing process for these types of highly polished orthopedic implants. So this is just to look into some of the kind of assets and some of the sort of products we make. Obviously, I said we're a contract manufacturer, so we don't own any product. We work for our customers to make their products. This is just a view of some of our inspection equipment, our Renishaw equator and previous some of our CMMs. We have obviously a range of kind of inspection equipment, and just showing some additive components now. So in terms of product and process design, it's our additive system here, but I think this is where the likes of nTop and the openness of the Renishaw system lend very well to what we do. Obviously, with the work we do, want to support our customers at different stages. So be it development or serial production, or moving from development into serial production, or working on like 510K data generation. So we need to have that capability. This is a little bit just to show on some of our automation for polishing here and belting of some femoral components. So a view in that, and also some automation around blasting. So I'm going to talk a little bit more about that on some of our research projects as well, which kind of highlight those. It's a nice example, porous structure made using nTop, printed in our Renishaw. So another key component of our sort of facilities here, particularly for additive, is our materials test lab, where we're able to do analysis of components on our microscope, do microstructure analysis, density measurements, both Archimedes and from cross sections that have been polished, mechanical testing such as compression testing and tensile testing here that you're seeing. So we do this for quality control, but also for the development phase as well. So we can do some functional testing of components, or if we're looking at new parameter sets, we can also work on, okay, what's the impact on strength or porosity or whatever it might be. So So just leading on from that, just in terms of where our services are in additive. So we like to think we're a one-stop shop for orthopedic innovators. So realistically, we're trying to help our customers at each stage. So as I said, if a customer has some prototyping needs and is trying to work on a concept, we can help with that in terms of doing design for additive manufacturing, design of, say, some porous structures, using nTop. Also help with then understanding how that might go from the prototype into the first 5-10K kind of builds for the data generation, and then moving into serial production. So we can move from each stage. And I think our materials lab and our equipment that you can see on the screen here obviously helps us, along with our 40 years experience in manufacturing. But really with additive manufacturing, it's a lot around the software, in terms of how we do that design, how we can create these really complex structures and efficiently print them. So that's really where nTop and Renishaw have really helped us out in terms of our growth in this area. So I've just listed some materials too, but titanium will be where our main expertise is in additive. We're also working on tantalum, and that's with Global Advanced Metals. So we've been developing the printing process for tantalum. That's both solid and porous structures, so like osseointegrative structures. At the moment, we can achieve material properties that are near or similar to bulk, so i.e. very, very good. So that's been quite good, and we've been using nTop again for design there, but a lot on our DOE designs, design of experiments, where we have kind of a range of different lattice structures we're going to try, or spacings, or whatever it might be. And then just to show you in terms of our research side, so we're very active on the research side. I've just shown two European Horizon projects that are funded by the EU. So we have Nomad and we have Cogniman. So we're partners in both of these projects. For the Nomad project, it's focused on dental implants, specifically trying to tackle peri-implantitis. Peri-implantitis is an infection of the gum and then the bone after implantation of a dental implant. It's relatively prevalent. It doesn't have good patient outcomes, so the infection can cause the need for, if left to go on, the need to remove the implant, which is quite invasive. So the project is really looking at how do you prevent or reduce the prevalence of this peri-implantitis, looking at zirconia and titanium. For Croom, our piece is focused on the titanium, and we're specifically focused on trying to make very, very porous, small porous structures where we can load those with kind of media that can hold drugs that can be released when we need it. So for that, we have to design porous structures that are much, much smaller than what you'd use typically for osseointegration, with smaller beams as well. So there's a lot of design work goes on there, a lot of design of experiments to try and optimize the structures, the printing parameters, this kind of thing. And then also we need to understand how that affects the overall implant. So both nTop and Renishaw have been very helpful in terms of what those platforms offer. So for nTop, we're able to use the custom blocks to, have a range of different sort of sets within our DOE, all made with the same setup. So if we have a particular way to make a porous structure, we can replicate that easily and just change the porosity level or the shape of the unit cell that we're using. So very easy for us to quickly generate a huge range of different designs and samples that we can then print. Similar for when we're actually trying to slice this and print it on the Renishaw, that CLI output that was talked about is super, super helpful. Not only because it allows us to have much smaller file sizes that are manageable, but also because it allows us to leverage the point exposure from Renishaw. And with that, we can create finer lattice beams due to the mechanism of printing, because we're just printing on a single point. For Cogniman then, we're leveraging, again, nTop and Renishaw here, but the focus is really on automation of the post-processing of metal AM, and also the development of a digital twin around the printing process. And a lot of that development of the digital twin is coming from leveraging the data from the process monitoring that the Renishaw output. So, i.e. the melt pool data, the images as well that are taken during the build. and also the design data that we can extract from Quantum. So yeah, again, it's quite good there in terms of the level of data we can get from the system, but also the data we can get from the design software, i.e. Quantum. So there are two really nice use cases of where we use the software along with our normal like MPI and production work as well. And I've just shown here a nice example of some exemplar components from the Cogniman project with the nice Voronoi structure in there. So, but I'll hand it back to Sean. That's all from me. So,
thank you, Shane. Great stuff from everyone. Now we're gonna jump in to the Q&A session. I do see some questions here, and feel free to keep those questions coming as we're answering them. So first question here, how can nTop make laser powder bed fusion support structures? Slicing parts to .CLI or .SLI is not helpful without printing supports.
Yeah, so that's definitely a good point to mention. So I was showcasing that export just to kind of showcase the way that we could go about that, but we also have that option to generate support structures. So we have some kind of built-in blocks within nTop, such as manufacturing support volumes and manufacturing support beams, so that you can, generate those as well for exporting, so you can export the support structures in addition. And then we also have in the kind of same discussion I was talking about, creating those custom blocks for something like this, those reusable workflows. We also have some of those that we share with our customers that are specifically on support generation. So if you're wanting to work with something that's more of a branched lattice style, we have some specific blocks or custom blocks that our team has generated and we can share with you to apply to a series of parts. We have some kind of mesh-based ones as well. So we definitely have a collection of those. And I know one of the initiatives I'm working on right now is making sure we have a lot of those available on nTop Learn. But if you're interested, we can definitely kind of send some of that information as well.
And just to add to that, actually, from Croom's side, that was actually one of our initial questions when we started to use the software as well. So we found good support from nTop and good development of the software as we went over the last few years, but also the ability to do custom blocks allows you to generate your own style of support. So we ended up actually making some of our own custom blocks for specific types of supports we wanted to do, and then generating, like, say, random points across the surface where we could have those interact with the part and use, say, branch supports as well, this type of thing. So, but I should say another piece is that you can do both CLI and, say, a mesh. So within Quantum, we can import a CLI and an STL, we'll say, and have those overlay. So, and that's what we might typically do, where we just use the CLI where it's really needed for something that might be very heavy in terms of size if we were to mesh it, and then have an STL or maybe even an original step for the actual, say, solid portion where it's not going to be quite so heavy. So very easy to mix and match them. So a couple of ways you can go about it.
Great. Another question here. How do you specify the porosity of the lattice structures in nTop?
Yeah, so what we can do with the Voronoi lattice and with the, here, let me pull out some of those. So with the Voronoi lattice, for instance, I can define that using our random points in the body. So we can control that point spacing that I have up here defined as our point spacing for the lattice structure. And then for the periodic lattice, I have that also defined with my cell size. So we can go about and define that porosity. We also have a block that's a beta block that is lattice pore size. So you can also, for instance, for the Voronoi lattice, that is more of that randomized structure. So the cell size will not be the same kind of throughout. So if you place this in here, you can see a point map, you can see kind of that color visualization and see the ranges that you are getting with that porosity.
And just to add from Croom's side there as well, this is a really important question, because if we're trying to do a DOE, for instance, a design of experiments, and we want to have, say, 10 or 20 different pore sizes, we can actually have a custom block where maybe there's only 1 or 2 inputs, and that might be the pore size. And we can also within that have an output of the reported back pore size from the analysis, we'll say, of the Verona. So again, it lends itself very well for design of experiments or quick iterations.
Great, perfect. Next question here. Is it a challenge to have a scan/printing strategy for both solid and porous structures in the same build?
Yeah, so from the Renishaw's perspective, within Quantum, you're allowed to define parameter sets and styles based upon any volume, mesh, slice stack, CLI you may import, and they're all independent of one another. So similar to what Shane had alluded to, and I'm sure he'll have his own perspective as well from a practical use case, but you can effectively merge those bodies together and apply different parameter sets to each location or volume, if you will, as you so choose. And even within that context, the parameters you choose could be point exposure based and or modulated based. So from the perspective of Quantum, it's a matter of a little bit of part orientation and then a checkbox to kind of realign and pick which parameter set you want to apply.
Great. Question I see here in the chat from Alexander. Do you need to overlap the domains of the different design spaces to prevent any line-on-line defects?
Within Quantum, there is a tool to align space domains to enable or to mitigate that phenomena that you're referring to. Yep.
Great. Next question here. What are the challenges with additive manufacturing for medical devices?
Yeah, just from my side, I mean, some of the obvious challenges when we have very complex parts. So how do we deal with, say, very complicated components where we have like a lot of change in the geometry, or we have complicated porous structures that we need to try and print? So need to understand, the influence of the printing parameters, the influence of the design on their strength, on their printability, this type of thing. So that's quite a big challenge. And again, it comes back to being able to iterate quickly. So we have to come up with multiple different designs to work through that. And for us, I guess, with our materials lab, that also helps where we can work, we'll say, with the Renishaw and have openness in terms of doing DOEs and changing the parameters, work with nTop in terms of different lattice structures, and then be able to test that within the lab. So I think that's quite a big challenge. So
great. Next question here. I see when building patient-specific designs, is it possible to isolate a surface of an implicit and updated surface roughness? For example, the bone-facing surface I would like to achieve a surface roughness of X instead of having to post-process the item.
So definitely. So with the actual implicit geometry, we can kind of define certain areas using fields for planes and such. But what I typically see is a lot of this initial design is created within, your CAD tool, for instance, or it's a mesh scan or something along those lines. And with that, it's pretty easy to select a CAD base or select a portion of a mesh, and then we can convert that into an implicit and use that as a reference for applying that, that surface roughness. And there's a lot of different methods to go about that with fields within nTop as well.
Yeah, and typically with patient specific, it's going to be a CT scan, so it'll come in as a mesh, and then you can use, I think, architected surfaces. You could do like randomized textures on there or like regular textures. So it's actually really, really interesting once you get into that side of things. So to alter surface roughness based off the, say, nTop methods they have, and then to print that. So quite cool.
And even if you didn't want to do it with geometry, you can in principle do it with parameter modifications as well, potentially.
Yeah, there's a number of different ways to go about it. I think actually it's really nice to with nTop, Mandy, you might be able to speak more about it, but with the texturing of surfaces, you can do that in a kind of an architected way. So you could like create your own sort of architecture, like whatever you want to be on the surface. So
yeah, definitely. And we didn't touch upon this so much in this webinar, but a huge part of nTop is field-driven design. And so you can either, generate some type of equation that references that surface roughness. We also have some noise fields within nTop that you can use. And then you could also adjust it so you have a variable roughness. So maybe it transitions from one type of roughness and slowly transitions to another in different parts, or goes from one field to the next. So a really interesting and important topic for sure.
Great, great. Couple more questions here. What are the advantages of doing simulation in nTop versus external simulation softwares?
Yeah, so with running the simulation in nTop, we touched upon it a little bit in the demo and with kind of the discussion of custom blocks and being able to iterate, run through that DOE, but it definitely can save time, save that whole process by running through the design and the simulation within nTop. And I've seen a lot of customers also run this with nTop Automate. So you can connect nTop to Python or some other type of coding language, and you can run through a series of those different parameters and really determine which is the best lattice thickness or best parameters for your application. So having that kind of seamless process to iterate is a big factor. And then also, well, I touched upon kind of one method for running through the simulation. If you're going through some of those design experiments and you want to save some time, we also have other methods that instead of running through by meshing this entire structure, we can also have a specific kind of lattice mesh that we have that uses those points. We also have a homogenization method, and so both of those will save time as you're going through that kind of simulation iteration.
Great, great. And here, does nTop offer any services for designing a workflow in nTop?
Yeah, so good question. So I'm part of customer success with solution engineering, and that is a big part of what we do. So before joining as a solution engineer, I was an onboarding engineer in customer success. So our customers have the onboarding engineers to make sure that when you get started, you really have a solid foundation and can ask those experts with any questions you might have, help you through your first workflow. And while I was in onboarding, I also worked with the initiative to create nTop Learn. So we also have many courses on those long form, as well as kind of video trainings and test problems that you can kind of test your knowledge and make sure you have a good foundation of nTop. As well as, we have these webinars that you can just use even if you are not yet a customer of nTop. And then part of my role is working with some of our customers to kind of continue working with their workflows, answering any problems they have, as well as providing managed services. So let's say you want to create some type of implant like this, you kind of want to have that pre-built workflow, and then you'll adjust it based on your type of application. You can also have a solution engineer work with you to develop that workflow within nTop with those managed services.
Great, fantastic. Well, it looks like we're at time, so I want to thank everyone for joining us today, as well as our presenters. I hope that what you all saw here today can help you with your implants and also other medical devices. If anyone's interested, feel free to reach out to us here at nTop or with our colleagues at Renishaw and Croom, and we'll be happy to help. Hope everyone has a great rest of the day.
Great. Thanks so much.
Thank you, everyone.
Bye-bye.
Thank you.